Great. Thank you, Andy. Okay, so I'd like to open the floor first to anyone who's online right now who might have a question about the videos that they've seen or something that's come up in the Flash talks. If not, I will go to some of the other questions that were left under the videos.
There's a raise hand button on the chat window. If people are interested, they can just raise hand or
Exactly. And Nathan is demonstrating that beautifully.
And to be clear, that raise hand feature is under participants. So if you're not seeing that, click the participants button, and then you'll have the various icons you can click to say speed up or slow down or raise your hand.
Got it. So Nathan, do you actually have a question?
Yes. Yeah. Thank you.
Sure.
So it was more of a discussion point, really. One of the things that I perhaps didn't present very well in my garbled rescuing of Ian's overview is that a big thing at Exeter is to keep a very close connection between the Earth climate model, which is being developed by several hundred scientists at great pace, and exoplanet version. There is no real exoplanet version. They're the same model. Everything gets munged together. Now that's great and it brings lots of benefits and I'm very committed to that, but it's been incredibly painful in many ways as well to try and keep pace. And I wonder particularly from Francois and from Michael Way, they also have these sort of models that can be used for Earth climate and exoplanets. And I wonder what your experience of trying to keep that going was like and whether, well, basically, do you have any tips?
Maybe I can start. What we've been trying to do is to keep a very common, this has required some effort, but a common dynamical core and overall running program. The system itself is about the same, not exactly to be frank. Then the physics, so we have really a separation in our, I think it's probably true for most of you, but the dynamics and the physics is quite separated. So the physics itself is independent. Nevertheless, we try to use the same philosophy and there is a common heritage, so that what I mean is that if you want to implement, I don't know, the latest boundary layer scheme from the Earth in your planetary model, for us, your question is also valid for Mars, Venus, and so on for us. Not everything is united. Well, then it's not too difficult. It's not difficult. And my philosophy will be to say that keeping everything together in our case would have been a very difficult thing because yes, we will have millions of Fortran lines, Fortran indeed, and lots of options. And so we had the same kind of questions during our past 20 years development, but it's usually, for instance, I don't know, when we started the Pluto model, we have a Pluto model, we separated it from this was derived from the generic model and we had a discussion, but in the end we separated them. Now we want to join them again. So we have the same kind of problem, but okay, the conclusion is we did not try to keep the Earth model together with the model. Nevertheless, one more thing, we still try to be together, and our chief engineer, Ewan Milur, is active as well in our planetary science team and in the Earth team. It's not a very big team, we're not that big. And he attended all the meetings and he's also, so it's very important to keep some personnel involved in the two developments indeed.
Yeah, I think that's a very good point. If I could just come back and agree with that, where however you do it technically, so with the we have like a repository for the main code, and then we have repositories for configurations, and that kind of helps a bit. You can, if you're at the Met Office, you can see, for example, a setup for GJ1214B. You probably won't really know what it means, but it's available. But actually more powerful than that, to agree with you, Francois, we've had some secondments where the Met Office staff, like Ian, who works at the Met Office, has come and joined us for a while. And although we're not physically co-located, that human connection between the two, I think, has been much more powerful. And yeah, I'd really agree with that, keeping the people communicating. Because for me, exoplanets is what I'm interested in, but I'm also interested in trying to see how that feeds back into our understanding of Earth's climate. So it's very important to try to keep that connection.
I want to add one more point, sorry. is that I think there is also a danger in being too close to the Earth model. Is that since we've been trying to develop this generic model, we have been super careful to, in some ways, start from scratch and avoid all the empirical and parameters that has been tuned for the Earth too much. And so that's why, for instance, a good example is the convection scheme. Our lab, half of the lab is working on Moss convection scheme and subgrid scale design, and it's a big activity for us. In spite of that, initially we decided, oh, let's not use that. After talking to them, they say, no, we tuned too much for the Earth. And we started with something much simpler, conserving energy, everything, but not too fancy, so that we didn't want to assume too much all the planets will be like the Earth. And what I'm saying is true for everything else. I don't want to have something too Earth-based in our model. I prefer to do something simple, different, and then maybe sophisticated it. But I think it's important to avoid being too close to the Earth model. But that's our philosophy. I enjoy also the fact that some of the other models are really close to the Earth model, and we try not to be.
How about you, Mike?
Yeah, I mean, I think we have this problem that we're a small group. The GIST GCM that does the Earth intermodel comparisons is probably one of the smaller CMIP groups that participates anyway. And we're a small group too. And so we basically have to work with them. And like Francois, we also have people that work in both groups. So our core developers work on both sides of the house, and there's very tight communication. My core developers go to the Earth development meetings every week, and we keep a tight connection about that. Francois is absolutely right that we have this problem that many things are tuned for Earth, but there's just no way around it. So he's right, we do spend a lot of time finding hard-coded stuff in the model. I'm not saying it's a pleasant experience, but I think there's just not much choice for us to get around that in a sense. But in some ways, we have been able to feed back to them too, because we have found some small errors, bugs in the Earth climate model because we pushed the model to dynamic regimes it never was designed for. Again, it's really designed for very specific, dynamical regimes and heating and all this kind of stuff. So in that sense, they have benefited from some of our pushing. And then we can update the development cycle. So it's the compromise we just have to make given the size and our funding levels at the moment anyway.
We have a very similar experience. So there are several bugs that we found throughout time that we fixed. And I think everyone on the call probably understands and agrees with Francois's last point about needing a hierarchy and needing lots of different types of models, right? There's no one way that's just going to rule them all. I'm not convinced by that. So,
yeah, agreed.
And if I may add to what Mike just said, we are trying at GIST to have we have two different ways of make the model Earth-like. One is that we are using empirical parameterizations and tuning factors, etc. And the other is by using certain components that we can simply turn off when we don't know anything about them for another planet. So as an example, of course, Moss convection is a good one, that there are some subgrid scale parameters there that are tuned for the size of the grid for Earth. So they can only work as expected when the grid size is exactly the same in kilometer size in some other planet. And there are other things, like, for example, the tides in the ocean, which we can completely turn off when we have no idea what happens with tides in another planet, that we don't know whether they have moons or whatever else will cause any tidal dynamics. So, yeah, I guess that this is a known problem, and the balance between what Francois said, that you don't want to stay close to Earth because you want to avoid as much as possible the tuning. And then the other approach that is Earth is the only planet that we can actually compare against something. And then there are people that believe that you need to understand, it's better to have some small Earth tunings, and then that might give you a little bit better understanding at some cases, but in some others not, rather than having some simple physics that will be separate, that will be either way more loose in terms of results when you go to different worlds. And I don't think there is an answer on which approach is the best.
Can I say something?
Sure, Ravi, go ahead.
Yeah, I was just going to say that, connecting with Earth GCMs, when we are doing the exoplanet modeling, either with ExoCam or with Rocky 3D LMD, the Earth case is a subset of the cases that we will be doing for exoplanet work. So aren't we already connected to Earth-based modeling when we are talking about exoplanet habitability or exoplanet atmospheric modeling?
Well, just to answer that, I guess if you're saying that Earth is one of the continuum of potential planets, then yeah, absolutely. But I suppose the key is just knowing exactly what your code is doing. So, and this is where model hierarchies are useful. So as Francois was saying, when I'm running a hot Jupiter, I don't have the Earth-tuned mass flux convection scheme turned on. Of course I don't, because that's very tuned to Earth and it's a moist convection scheme, which I don't need. So you can keep the model framework connected, but it's just about trying to understand where you have a piece of physics or parameterization, how valid is that going to be? What are the, if you push that into an extreme regime, is it going to start giving you nonsense? And that's the kind of thing that inspired Dennis's work, which hopefully you've had a chance to see the pre-recorded talk, trying to find a range of treatments for convection and some ground truth in the absence of a probe on GJ1214b or et cetera, some possibility to tie it to something.
Great. Okay, so I see that Russell has had his hand up, and so I'd like to go to Russell.
My hand's really tired now. No. I had a question about the TIE simulations. So if I caught it correctly, first I just want to check my understanding. It looked like between the 4 different models, in the dry simulations, there were 3 models that kind of sat in one dynamical regime, and then the Rocky 3D was in the other dynamical regime. And then if I understood it correctly, in the wet simulations, they swapped places. Is that correct?
So it is correct for Ben 1. So we have a first case, benchmark dry.
For Ben 1 and Hab 1, yeah.
Yeah, but for Ben 2, when we are also dry, but with only CO2, then the only one that is not in the same dynamical regime is ExoCam.
I see.
So we are really at a transition, and so it's very difficult to understand. And so there are probably several mechanisms that can explain that. So the planetary boundary layer parametrization, or your temperature will be stratified or not, will really change the Brun-Weisler frequency, and so will change the Rossby number. We have also the height of the tropopause will depend on on many things, on the intensity of the convection, or also the average temperature of the troposphere, and depending on this height, you change your scale height of the tropopause. You also change the Rossby number. And so there are a lot of competing effects for that. We are not sure how we will be really able to isolate one effect or another, but indeed we still try to investigate why in some case, I think in the dry case, Rocky 3D rotates slower, I guess, and in the moist case, it rotates faster or something like that. But again, yeah, it's, we didn't really expect that at the beginning, but TRAPPIST-1E is just at the edge between the 2 rotations. And even if you look at the Denis Sergeev work with so with only the same GCMs, if you change a little bit one of the parameterization for the convection, or even I think the boundary layer, you move from a fast rotator to a Rhines rotator as well, just with the same model. So I think it's a great case for an intercomparison, actually, because
Yeah.
it's so sensitive. But ideally, I think we will get a better agreement between all the model if we will have been just at the middle of a regime. If we will be well inside the Rhines rotator or slow rotator, we will really have a great agreement between all the model. And so I think TRAPPIST 1 is really a peculiar case, but interesting.
Yeah. Yeah. Thanks. Yeah.
Sure.
Is there anyone else online who has a question at the moment? If not, I will turn to some of the questions that were previously asked. Going first to the LMD model, Francois. Mike Way, you actually had a question for Francois. Would you like to ask him directly?
Okay, let me go find my question. I think it was quite technical. I don't think there would be that much interest in it for everybody else. It was more of a Mars-related question because we've been thinking about how to deal with different kinds of ices in the clouds and the microphysics involved. So I wrote basically related to the Mars model, you support CO2 ice and H2O water and ice clouds, I assume, in your model. And I was wondering how you handle the complicated microphysics of these clouds, since the clouds will overlap in the same grid cells, and hence it's likely, like, for example, that the CO2 ice clouds will nucleate on H2O ice grains in polar winter. We see that, we believe. And then you have high altitude tropical CO2 clouds that nucleate on meteoritic dust, H2O ice, and possibly surface source dust. It's very complicated. So I'm curious how you handle that. If it's too complicated to explain, don't worry about it. But that was my question.
No, but very quickly, we stay simple in some way. In the philosophy has been a lot to represent all the unknown details of the microphysics by just prescribing an unknown number missing ratio of cloud condensation nuclei in some way. And then we distribute the mass with that. And if you think about it, you can do a lot doing that. So you don't know the reality, but you can bracket the reality. Usually you find that even by exploring several, even a lot of order of magnitude, you get about the same results. So that's the good news. And doing so, I've been quite confident that you can do a lot of the details of the microphysics. The only thing that you don't do well is when you have really supersaturation induced, but that's already really an order. It's a detail compared to what you say. So to conclude, we just use this. We explore the sensitivity to this peak parameter we call NMIX. Is the number mixing ratio of CCN, and that's enough to explore the range of possible to try to bracket the reality, and that's it. And in addition to that, of course, you have a problem when you have when you start to have coalescence. Then it's you have to take into account the fact that we're starting to, if you want to make droplet or big things, and they will. So that's another process that we simply also simulate.
Okay, great. Thank you so much.
Okay, Prabal, you have a question.
Yeah, sorry about coming in late on that. So this is actually about the TIE habitable cases and intercomparison. So when you look at the continuum regions, do you see differences between the different models in different continuum regions? Because I'm sure the way you calculated the SNR was based upon some type of relative to continuum peak for that carbon dioxide signature.
Yeah, so we always, it's a relative difference. So I always select the wavelengths of the peak for the CO2 at 4.2, 4.3 micron. And after I look for the minimum in the continuum. And so it can indeed vary depending on the model, but I think it was very, very, very close for with the wavelengths of the minimum, I mean, on the spectra. But yeah, it's but the level is really driven by clouds. And I didn't mention in my talk was interesting actually is that we think it's going to be mostly stratiform clouds. Probably when we will write the TIE paper, we have to separate the convective and stratiform clouds. But so everything that's happening at the substellar point is so for the convection itself is really dependent on the convection scheme, but it seems to not influence really what's happening at the terminator, because as Francois mentioned, at the substellar point with the LMD, you have the convective adjustment. Usually you have a slightly weaker convection with respect to the other model. And so LMD produce less cloud at the substellar point. The cloud deck is thinner. But LMD actually has much more clouds than Rocky 3D in UM at the terminator. And so I really think it's because actually stratiform clouds are dominating there. And so that's really the cloud microphysics that play a role. And that will be probably true for even slower rotator, I think.
Thanks.
Sure.
Great. So let's see. I think we may have something coming back to LMD from the Slack channel, and please correct me because I'm almost certain I'm not going to pronounce your name correctly. Imeric Spica? Are they on?
No, sorry, apologies, Linda. I passed that note on to you. They said they had a question for Francois about Dynamico, but they're not on the Zoom. Let me ask in the Slack and see if I can relay that question.
Okay. Okay. So in the meantime, let me come back over to the talks. So Thomas, there is a question for you from Emmeline Beaumont. She says, I have a question about the rotation regime discrepancy. Did you consider simulating the cases with another rotation, either faster or slower, to try to have all the models in the same regime? Also, what are the differences between a convective adjustment scheme and a mass flux scheme? And lastly, and not least, is there really no way of telling which GCM is closer to the truth?
Okay, that's a really great question.
It puts you on the spot, but.
Okay. So for the first one, that actually would be something that will be probably at the outcome of TIE, because that was close to Russell's question as well. We knew that TRAPPIST-1E was roughly at the edge of different rotation regime, but we didn't know that was really right at the edge. And so we will definitely, I think, wrap up the TIE intercomparison only for TRAPPIST-1E, but that's definitely worse indeed in the future to continue this kind of intercomparison thing that actually belong to the Cuisine framework, and we are going to talk later this week. And so, yes, I think we will need to do an intercomparison also right in the middle of the Rhine regime and also in a slow rotation regime. Definitely worth to compare that. For the second question, I think I'm probably not the best to answer differences between a convective adjustment and mass flux. Maybe one of the GCM developer from one of the 4 GCM can answer that better than I will do. And for the last one about the which one is closest or further from the truth, I think it's very difficult to say without having data from James Webb or future ground-based observatory, because I mean, we can still compare this 4 model for Earth and compare with data, but that's not going to help us really to know if we closer or further away from the truth for TRAPPIST-1E. So I think that's really of course, the main difference that we have here for TIE, if you compare with an intercomparison on Earth, because on Earth you can still benchmark with the real data and know which model is closest or furthest. But here we can't. We just basically now have these 4 GCMs. Hopefully we'll have more GCM in the future that will join such effort, and we can basically now have an uncertainty or an error bar or n members, if you want, where we can really estimate the observability of a given planet, but I think we can't know which one is closest or furthest for the truth.
Thank you, Thomas.
Sure.
Maybe I have a follow-up question. Don't the bodies with atmospheres in the solar system can help us compare, and they might be easier to do than Earth and bring more, to the table?
Yes, that's a great point. I'm not sure if every model will be able to do, like, I don't know, even Mars. I'm not sure Mars could be relevant for to compare with the dry case on TRAPPIST, 1E for TIE maybe. But I don't know if we want like Titan, for example. I don't think the 4 GCM are able to do Titan right now. So that's also the issue that we don't have that many benchmark planet or moon that we can use to do this comparison.
In some way, if I may, I think it would be a good goal. It's easy for me to say that, for all these models to try to simulate other planets in the solar system, because earlier days someone said, oh, Earth is the only planet we have to test our model. It's not true. And there is no reason that, no fundamental reason based on what I've heard and see from the other model that it should not be too difficult to simulate some way Titan, Mars. Venus is a little tricky, but why not? I think it could be at least tried, and it could be a good project for everyone. I want to add something about the question by Emmeline about the mass flux and convection scheme. So very brief, I have two things to say. First, very briefly, when you have convection, that means you have quite large scale convection cell building because of you have ascendance and descendance and of cold and warm air, sometimes because of condensation that release latent heat and so on. You can simulate that by just mixing in at the scale of the grid point, if you want, of the mesh in your model. That's a mixing, simulating the effect of this. But in reality, it's not the way it is. In reality, you have an ascending motion in one column and air descending in the rest of the cell, if you want. So you can represent that by having a kind of pipe where you, in some way, simulate the fact that you have a pipe of air moving up and then releasing, we call that detraining, whatever has moved up and then going down. So it's a different way of parameterizing a reality. And the point I want to add is that even if we are in a very exotic situation, it's not hopeless. The reason is that you can study a very exotic convection system, like very hot planet, sun side of TRAPPIST, whatever you want. Even if it's very exotic compared to the Earth, you can try to simulate that with a very high resolution model, cloud resolving model, large AD simulation model, see what happened, and then parameterize what you see in the detailed model in a global climate model. And that's I think it's the way to go, and it's already starting. Maxence Lefebvre is presenting things about that, and I think it's for many processes. It's not because we don't have an example on the Earth that we have no way to tune and prepare a parameterization. We can use high resolution model to do that.
Thank you.
Great, thank you. Thomas, there is another question for you. It says that this is from Gabriella Geely. She says that you mentioned in your video that the top of the model at about 1 Pascal is not enough to fully capture the transmission spectra, so you extend it a bit higher. I agree with this extension, however, it doesn't seem to have a strong impact on the transmission spectra of the strongest lines, only a few ppm, right? Which is probably lower than the sensitivity of most instruments. I'm wondering if the computational cost of this extension compensates the achievement of better observables. Not sure about that in this particular case. What do you think?
That's it's a very good point. I think, I think Martin actually showed that in his presentation. It is more clear for the CO2 planet because the mean molecular weight is heavier, and we really, in this case, have a massive truncation of the CO2 line because when you have the model top at something like 40 kilometers, or it's way too low to really capture the whole atmosphere in transmission spectra. And in that case, I think we really have tens of ppm maybe 30 or 40. Again, I think we need to look back. One of the figure we have done on that for the dry cases with CO2 and the moist cases, but the effect was pretty strong for the CO2. For the modern Earth atmosphere, so dominated with nitrogen, the impact is much smaller. Indeed, it's probably something you can't detect. It's way below the noise floor that we will expect from James Webb of something like 10 ppm or so. But for CO2, yeah, I'm definitely convinced we need to really go. So I think in this case, I've been up to 10 to the minus 10 bar at TOA. So the problem also to do this extrapolation, we have to make an assumption. And so we have assumed just an isothermal atmosphere up to the top. And we have fixed the mixing ratio of the dry gas, and just we did not extend water and clouds, of course. So it's probably not a good assumption at all, but it's the best we can do, I think.
Okay. Emily,
Thank
you
you,
have
Thomas.
a follow-up? Oh, sorry.
Sure.
Thanks.
Emmeline, you have a follow-up that you just posted in the chat?
Yeah, I was just continuing my thoughts from earlier and wondering, you know, we were talking about comparing Mars or everything. I was just wondering naively if it wouldn't be easier to compare for the gas giants like Jupiter or Saturn. Do you know if efforts were done in this way? I don't know.
Can I come in on that? So some of the problems with the gas giants is for the terrestrial planets, they're very heavily forced and damped by surfaces, and the rate of forcing throughout the atmosphere is reasonably strong. For the gas giants in our solar system, the forcing and damping is very weak. So they're actually much harder cases, I think. And if you look at the efforts on Jupiter to try to get the simulations to produce, there's the whole debate between whether it's a weather layer, which of course is now through Juno coming to a sort of conclusion. But they're quite hard to get right dynamically compared to the terrestrial planets. So I think perhaps they're a more difficult case, especially the ones where the flows are deeper into the gas giant.
Okay, thank you.
Thomas, you have your hand raised.
Yeah, actually, I was going to ask a question to the people in the four GCM. So Eric for ExoCam, François and MDG, Rocky Sweeney Mike, and Nathan, or every other people in the team. What would be then the planets in the solar system that your model would be able to simulate? So that if you have to think about such kind of intercomparison, what are the ones that you can possibly do that we can maybe hopefully have an overlap between the four model?
So for the we have tentatively started running some Mars simulations. It's just a question of resource, really. We have gas giant exoplanets we're working on, Earth stuff, and terrestrial exoplanets. Moving into solar system has just been a matter of resource, but it's something you want to do. We're thinking about Venus, Jupiter, and Mars as our main targets, but Venus radiatively, as people on this call will know more than me, there's a lot of work to do to adapt to GCM, to what's happening in the atmosphere. And then Jupiter is quite tricky for other reasons. So for us, I think Mars is probably the easiest one, perhaps, but I am not an expert on Mars, so maybe I'm oversimplifying it.
I think just to add to what Nathan said, we also started adapting to the Titan's climate. So I think, you know, since Titan has a very similar range of processes, albeit with methane instead of water, of course, I think it would be one of the best targets for terrestrial GCMs.
Thank you, Dennis. Very good point. I completely forgot we're doing that. Thank you.
Thank you, guys. But other GCMs?
Hi, Thomas. This is Eric. I'll chime in. So there's a very well-developed Mars Cam version that I'm currently inheriting and trying to port up from circa 2005 Cam 3 centric model into something that can take advantage of to the more recently developed dynamical cores and moist physics in some of the more recent versions of the NCAR model. And then there's also a fairly well-developed Camp Titan, which has kind of fallen out of use. It's you can find it available online, but so we could do Mars and Titan, but again, it's it's an issue of resources to be able to compare all those. And I guess in its relevance back to exoplanets, I mean, I believe that comparing Titan and Mars GCMs would be an amazing project to do, but it's unclear how that would, to me at least, how that would really play back into the TIE project exactly, just because there's unique pieces of physics that will be in the Titan, like Titan Cam and Mars Cam, which are currently unique from the exoplanet version, ExoCam, that we run. And I don't know if that's the same or different in other models. I mean, that's one of my projects currently, is trying to harvest some of these other physics pieces in Mars Cam, and then perhaps also Titan Cam, and try to collect them all together. But I mean, that's a large project, and we talk about small teams. NCAR has no interest in exoplanets, so at the moment I'm kind of a team of one. So I do what I can.
Thanks, Eric. François,
as for us, of course we have a dedicated GCM for most atmosphere in the solar system, but the challenge here is to simulate them with the generic model, the one that is supposed to do every the planets. So we have tried to do that for Venus, Mars, and even Titan, and we can do everything. But my point is that it's not really that we need the intercomparison, but I encourage every model to simulate these planets, because we have observations. So you can compare what your model do with actual observations. No need to organize intercomparison. Just look at take the data and see if your model, assuming if you take Mars or Venus or Titan as if it was an exoplanet, you have data. So if you take all the data you have, can you simulate what's going on? That's a good challenge, and I encourage everyone to do that.
Yeah, I completely agree with Francois. We have them, so we don't have to do any intercomparison in that sense. But I would say, at least for us, we do have kind of a beta version of a Mars model. But while Mars looks simpler on the surface, it's not. I think Francois knows that very well. And I touched on it a bit earlier about this issue between water ice clouds, CO2 ice clouds, and the radiative effects are important. Dust is important, dust lofting is important. That changes the radiative balance of the planet. We're putting a new dust model in, for example, into our Mars model now to look a bit more realistic. We're probably at least a year away from having proper CO2 ice clouds. So I think for us, Mars is our next solar system planet that we can model accurately. And when we get those changes in for Mars, I think it will also be pretty straightforward to do Titan, because some of the changes we're making will be able to feed over into that. To do modern Venus, as I replied in one of the queries for the GCM, we're very far from that because of dynamical core issues, radiative transfer, dynamic regime. It's very difficult. What I need to do is hire a Sebastian Lebenois for a few years. So if you want to put him on loan to us, Francois, please let me know. But for now, I think we're very far from. And modern Venus models are very difficult to do from everything I've seen. They look very challenging. Anyway, our 2 cents.
Just to add something on that, if I can, the one thing that I think we have to be clear about is the fidelity of the question we're trying to answer. So on Earth, we're really trying to answer questions like, will it rain above my head tomorrow? And for Mars and Jupiter, etc., we have observations. So the question is a much more detailed question. For the exoplanet stuff, this is much more of I guess maybe a tipping points regime. This is much more about, one of the most interesting things to come out of the TIE into comparison for me was this serendipitous discovery of, that seems obvious and reflect and simple, that TRAPPIST is right on the edge of this kind of large scale boundary in the change in the circulation, and that convective treatment can change that. So really with exoplanets, we're going to be looking at big things, big changes to the climate. And so it's a different type of question in my review. So I do want to model solar system planets, but I'm not going to rush to divert all of my efforts to doing that, because there's lots of people doing that. I'm interested in trying to look at the big tipping points that control sort of large scale changes in the climate. And ultimately, I think for a parameter space as big as we have, we need a whole range of different approaches.
Thank you.
Okay. So before we end, I saw earlier that Gabriela Suissa and Prabal had their hands up. Do they still want to ask questions before we go to coffee?
Gabby?
Yeah, I had a quick question, but well, I don't know how quick it'll be. I guess it's a little of a naive question, but do we ever expect the GCM models to truly converge on a universal truth that works for a bunch of terrestrial planets? Or like, is the goal to iterate on each other and to make changes to get the same result? Or would that baseline be very different and highly finely tuned for every single planet that we find? If that makes sense.
If I may chime in for a minute from the Earth model intercomparison perspective, nobody expects to get the same result. What you look for is consistency across models. So even if models arrive at an answer in a slightly different fashion, the fact that they come up with roughly the same response is a sign that you're on track in terms of your understanding of the physics that are involved and what should go into the models. So don't let the perfect be the enemy of the good enough. There's always some sort of trade-off that needs to be made. As long as you recognize what that is and acknowledge it, I don't see that there is a problem with people coming up with slightly different answers. And that is, by the way, how we end up discovering which models are handling certain parameterizations perhaps more realistically than others, right? Just by using whatever we have in the models, and that can drive future development and improvements.
Thank you, this was helpful.
Sure.